Alright, and now we go into Chapter 9, which is going to be about sampling distributions and confidence intervals for proportions. So in 9.1 we talk about the distribution of sample proportions. So a sample proportion, you can think of it like a percentage. So let's use an example. Let's say that we ask a group of DMAX students, and again, we have to be very smart about how we collect those students, and we talked about in class simple random sampling. So we'd probably want to organize them by student ID and have the computer randomly select 30, 50, 100 student IDs, and then we would send them a questionnaire. And let's say the questionnaire is about financial aid. So let's say that we ask them if they use financial aid or not to pay for their DMAC education. And let's say that the proportion that we're interested in is how many students answered no. They use no financial aid whatsoever. So basically, they or their parents are paying for their education. And so the proportion will just be the percentage of students that responded, no, I used no financial aid. So that's what we're going to use for our proportion P. So we're going to call the true proportion P. And what that means is of all DMAX students, so again, all the students across our 6 campuses and online, the 30,000 or however many there are, we're going to say that the true proportion is P, which means that's the percentage of students across all DMAC campuses that received no financial aid. They paid for college themselves. And to follow along with the slides, we're going to say that that P is 0.2, which means 20%. So 20% of the students we're going to say use no financial aid. Now this is completely made up, so don't quote me on any of this. We're just saying for illustration's sake, 20% is the true proportion across all DMAX students. Now, what we would have to do is we would have to take samples. So we would have to ask, maybe 100 DMAX students from our random sampling what they did for financial aid. And the proportion that they report from that sample might be 0.21 or 0.24 or 0.18. It's going to be different most likely, but it's probably going to be close to this proportion, the true proportion of 0.2. Now the tricky thing is this true proportion of 0.2, we will never get that number. So we're not going to talk to every DMAX student, so we're not going to actually know what that is. So what we're going to do is we're going to take a bunch of samples and we're going to see how they come out. So some might be 0.18, some might be 0.19, 0.2, 0.21, etc. And in fact, what they did here in the slides is they said, okay, we took a sample size of 1,000, so they literally talked to 1,000 people. And then what they did, and we're going to go into this later, but what they did is they sliced this in. They basically took combinations of these different answers, these 1,000 answers, and they created new samples out of that. It's an interesting technique. It's pretty advanced, so again, we'll talk about it later. But they did this a bunch of times. So they created, out of 1,000 answers, they created a bunch of samples. And then they plotted the samples' proportions. So again, every sample that they had out of those 1,000 answers would have a different proportion. And then they plotted all these different proportions on a histogram. And what happens is the histogram of proportions looks like a normal curve. And it's centered on the true proportion P of 0.20. So what they found out was out of their 1,000 answers that they sliced into a bunch of samples and mixed and matched the numbers and created new samples over and over and over again with the computer, they found out, hey, it is very likely that the true proportion is between 0.24 and 0.16. And that most samples, in fact, so between 1 and 2 standard deviations, 68%, are between 18 and 22%. All these sampling distributions are called p hat. They have a little hat above it. So in our example, if we wanted to do this without the computer just kind of coming up with these numbers, what we would do is we would talk to thousands a lot. So let's say we talk to 100 DMAX students. So we would talk to 100 random DMAX students over here and 100 random DMAX students over there. And we would do this a bunch of times, and we would get a bunch of different proportions, and we would plot them up and see how they looked on a histogram, and we would say the center of that histogram is the true proportion P. So we can also think of this as success and failure. Now in our financial aid example, it maybe doesn't make sense, but there's lots of conditions where we can consider it a success or failure. So you win, lose, you have the disease, you don't have the disease, yes, no, that sort of thing. So we can say success and failure. Well, P hat, the proportion of people that say yes to financial aid, well, there's a relationship to those who say no. They both have to add up to 100%. So if I have 20% of my sample saying yes, or if I have 20% of my sample saying no, we didn't receive financial aid, that means 80% said yes. That's pretty simple. We've talked about that. So what we basically want to do is, from all these samples that we take, and again we're going to take a lot of them if we can, or use a computer to bootstrap to create many samples from a few, and we are going to create a sampling distribution. And again, that should be a normal curve that's centered at P, the true proportion, and it has a standard deviation of this equation. So we should have a normal curve centered at P with a standard deviation of P hat, and all it is P times 1 minus P, so in our example 20 times 80 over N. So if I talk to 1,000 students, N would be 1,000. And what we find out is that the standard deviation is about 1.3%. So we would say, we feel like 20% plus or minus 1.3% of students would have said, no, we don't need financial aid for our schooling. And again, we talked about this before. So if I take a bunch of samples of students, groups of 1,000 here and there, or maybe groups of 100 might be enough, that's called sampling error. And again, it's not an error. It just means that out of this 100 students, it might have been 20%. And then the next 100 students, it might have been 21%. And the next 100 students, it might have been 18%. So it's just really the variability in the sampling proportion that we're talking about here. And that's to be expected. I mean, if the numbers were all the same, then it would be suspect to be, I don't know if this is accurate. And so what we're going to do then is we're going to create a normal model. This just says here's a normal model that's centered at P, the true proportion, and the standard deviation is the square root of PQ over N. So again, Q is just 1 minus P, or if P is 20, Q is 80, that sort of thing. Okay. And then here's what it'll look on as a normal curve. So you'll have, after all, you take all those samples, the true proportion is P, and then you go away from P with one standard deviation increments, where the standard deviation is square root of PQ over N. So how good is it? Well, it's very good, actually, as long as the sample size is big enough. And we'll actually spend a lot of time later talking about, well, just how big is big enough. For our argument here, we would say if you get a sample size of 30 or more, and you do enough of those sample sizes, so again, I'm going to take 30 students here, 30 students there, 30 students over another place, and kind of get enough samples, then it should approximate the normal model when I find all those proportions. Now there's some assumptions and conditions we have to meet. One is independence, so the sample values must be independent of each other. And basically, the way to ensure that, it should be random. So the more random you are in selecting your students. So again, what I said before was, well, how should we do it? We should have the computer select from our student IDs, 30, 50, 100 students at random, and that will help us ensure that that these are independent. So the way that would fail is if you start talking to students who are related to each other, right? So if there's a rich family and they have 4 students at DMAC, all 4 of them are saying, no, I don't need financial aid. Well, if all 4 of those students are in your sample, now they're not independent because they have a condition in common, being that they come from a wealthy family. So you want to try to avoid those sorts of interdependencies. Sample size must be large enough. Again, we'll study this in detail of what large enough means, but for now we can say 30 is probably good enough. And then random. So we want to make sure that the way we collect our information is done, the way we select people to be a part of our information gathering is random. 10% condition, that's a new one. We haven't talked about that. Basically, you don't want your sample size to be bigger than 10% of the population. So, if our population of DMAX students is 30,000, you don't want your sample size to be bigger than 3,000. And basically what happens is you start to worry about independence breaking down if you get to be too big. Now, in most populations, you're talking thousands, hundreds of thousands of people, maybe even millions of people. This is a pretty hard condition to break because you have to start talking to lots and lots of people. Then the success failure condition, that's a new one as well. Basically, you want the sample size times the probability of success and the sample size times the probability of failure to be greater than 10. So this kind of tells you how big your sample size needs to be. If your probability of success is 0.2, then n has to be at least 20 to be greater than 10. And if q is 0.80, then n has to be at least bigger than 8. So we would say it has to be at least 20 based on this condition here. So you can kind of decide on if you know, having a sense what your p is, how big of a sample you need. So here's an example. This will help us see the numbers and how they work out. So this says a packet of seeds claims that germination rate is 92%. So that's the success condition. P, the success, is 92%. So P equals 0.92. Then our question is, what is the probability that more than 95% of the 160 seeds in the packet will germinate? So the first thing we're going to do is we're going to run through our conditions. Make sure our constraints are met and that we don't violate any of our conditions before doing our mathematics. So independence, so we have to ask ourselves, is it reasonable that one seed's germination is independent of another seed's germination? And we can assume yes, that it's probably one seed germinating does not cause another seed to germinate, or vice versa. Randomization. The sample of seeds can be considered a random sample from all seeds of this producer. So we have to decide, is this one packet of seeds random from all the packets of seeds? And we have to think, this producer of seeds probably makes thousands of these packets. Each packet has hundreds of seeds. So there's a good chance that our packet is sufficiently random considering all the other packets we could have chosen. Again, you'd have to be a little careful if you're going to test a bunch of these seed packets. You'd want to pick a packet and then pick the next packet randomly. So you wouldn't want to just pick two packets right next to each other, because if there was a bad batch or something, it could affect packets that are close to each other. So you'd have to consider how that's done. 10% condition, there's no way that our 160 seeds is going to be close to the total population of seeds. There's probably literally millions, maybe even billions of individual seeds. We're not even close to being 10% of them. Success failure, I'm going to multiply the success, 0.92, times how many seeds I have. And that says I need at least, that says I'll have 147, which is much greater than 10. And then our failure would be 1 minus this 0.92, so 92, 8, add up to 1. Times 160, so 12.8. So I have enough seeds is what this means. So based on these percentages and these amount of seeds, I'm bigger than 10, so I have enough seeds. So now we're going to find the normal curve. So we believe the true population, the true proportion for our normal curve will hover around 0.92, 92%. And its standard deviation is, again, the square root of P times Q over N. P is 92, Q is 8, N is 160, 160 seeds. And so we'll get the standard deviation is 0.021. 0.021. And basically what that means is we believe our seeds will germinate at 92% plus or minus 2%. Now what we want to ask is, what's the probability that more than 95% of the seeds will germinate? So now we're going to say our value of interest is 95%, so that's our p hat, minus what we believe the true proportion of germination is, which is 0.92, divided by the standard deviation, 0.021. So we say the probability that at least 95% of the seeds will germinate is a z-score of 1.43. Then we go to our z-table lookup, and we find the area for a z of 1.43. Now, z greater, which means that's going to shade to the right. The table is going to give us the area to the left. So we're going to subtract the table area from 1, and we're going to find that the probability that at least 95% will germinate